we chose for this week was the rope swing lab. In this lab, a rope swing pendulum was modeled with a real rope uh, that can be modeled as a spring, and an ideal rope, which is a taut or tension force rope. The goal was to see if energy is conserved using the energy principle and possibly explain why a rope realistically acts like a spring to an extent. For the conditions of the video, we used all our objects and forces to be considered within the system, and so for the experiment, nothing was in the surrounding. For the initial conditions, the mass was 70 kilograms, the initial position was negative 45.72 x, the initial velocity was 0, the spring constant K was 11,000 Newton meters, and the initial length of the rope was 45.72 meters. This lab used several different formulas for motion of an object and energy conservation. For the motion formulas, we have Fg equals negative mg and F spring equals negative ks times L hat. For energy conservation, we have delta K equals 1/2 mvf squared minus vi squared, and delta Ug equals mg times delta y, and delta U spring equals 1/2 K SF squared minus SI squared. Along with both of those sets of formulas, we also use the position and velocity update formulas, which is Vf equals Vi plus F net over m delta t, and Rf equals Ri plus Vi delta t. For an ideal system, like in the model we created, the energy principle would be 100% accurate and no energy in the system would be lost, since we included all of our objects to be all objects and forces within the system. Since this wasn't an ideal system with an ideal rope, there would be some energy loss due to forces that weren't included in an ideal system, such as drag force and possibly friction force from the rope dragging on the surfaces connected to. These first two screenshots of code are all for the setup. They initialize all the constants and variables used within the model, which are the mass, position, velocity, gravitational constant, spring constant, length of the rope, and the initial energy formulas that were used. And these other two screenshots are what were used in the looping part of the code to update all of the values and potentially create a model. The loop updates the spring, gravitational, and kinetic energies, as well as updating the position and the velocity of the object. Modeling ideally, the screenshot on the left is what it would ideally look like. Since the rope acts more like a spring, the next screenshot in the middle is what it would actually look like, except this model does have an exaggerated path due to coding error, but if it wasn't as exaggerated, it would be a relatively realistic path. And the model on the right is what the energy of the system should look like in an ideal system. In the end, for the most part, the energy principle did hold and energy would be conserved within the system in an ideal scenario. The other thing is that we can use a spring to model a real rope in a real world scenario. This is because depending on how taut the rope is, it can be treated like a spring with one spring constant used throughout the entire length of the rope.